So we will start the last part of this workshop with Pawel Wargocki from DTU Denmark with the role of air cleaning in infection control.
Okay, thank you very much, and thank you for staying so long with us. And this is the variant of the second day, and I asked a lot of questions during the first day and during the second day. So now it will be a payback time for you to ask me several questions after my presentation. So thank you very much for giving thank you for the organizers for giving you the opportunity for doing this. I have been charged to say about something that really is very difficult to talk about, and it's about the role of air cleaning in infection control. Well, the first presentation after lunch have made a lot of comments on that point, and I will be quickly jumping, and I'm sorry for quickly jumping in slides where there is a repetition, and I'm sorry for that repetition. We were not coordinating our presentation. So basically, I will start to say that there is a wild west of air cleaning, and it has been, and it is, and it will continue. And there are many reasons for that, but I will only focus on infection control. There has been a lot of claims, a lot of statements, a lot of positions during a pandemic and even now today on the effectiveness of different air cleaning technologies. I call it wild west because there is some of that has been somehow coordinated and has some reference, good reference, and there is some of that for which we really don't know whether this is true or not true. And we as the engineers have a lot of discussion about this, and we can get lost in it. But think about the normal consumer at the very end. Mr. or Mrs. Smith is afraid of COVID and they want to buy the air cleaner and they really don't know what to do, basically. So I hope my objective today is that I try to do the true story about, I hope true, we can discuss afterwards, about the effects of filtration and air cleaning on reducing the risk of infectious disease in occupied buildings. And in the brackets, I just say that with no potential of adverse effects. So I will be looking at different types of air cleaners and different air cleaners that may or may not create a potential adverse effects on people. So let's start with the introduction. So during the pandemic, there have been several recommendations regarding air cleaning, and these are two recommendations that are probably the most known of them regarding air cleaners and air cleaning. The one is by ASHRA Epidemic Task Force, and these are core recommendations which say that they, under point 2, they say that you should, besides providing ventilation rate, you should use combinations of filters and air cleaners that achieve at least MERV 13 or better levels of performance for air recirculated by HVAC systems. And also they say only use air cleaners for which evidence of effectiveness and safety is clear. And then the Lancet COVID-19 Commission Task Force also published the recommendations, and there were 4 recommendations, and 2 of them related to air cleaning. And one was just a repetition of what is in the ASHRA epidemic task force, is to upgrade air filters to minimum efficiency reporting value of MERV 13, and then supplement those with portable air cleaners where needed. So these were basically the recommendations. Those recommendations were in following basically the recommendations of other recommendations for defining so-called non-infectious air delivery rate. Sometimes it is called equivalent clean air. Sometimes it is called equivalent outdoor air. It's basically the air that does not contain the virus or is free of pathogen. And basically, the Lancet Commission published the report in November 2022 that defined 3 levels of those non-infectious air delivery rates, and that were corresponding to 4, 6, and above 6 air changes per hour of equivalent outdoor air. I will come back to this point because that is very important in connection to air cleaning effect. And recently, this week, I think this week or last week on May 12th, last week on May 12th, ASHRA published the standard for review, ASHRA standard 241, in which those equivalent clean air delivery rates were proposed. And at the same time, CDC published recommendations for 5 air changes per hour. So why I'm talking about filtration, but basically it is very important to have that reference because this is the target levels of dilution that you need to obtain. So if we think about those target levels, we have to remember that those target levels, they refer to the aerosol transmission in long range. So what we are talking about is a long range, not the short range. So it's a far field, not a close field. And these are the aerosol transmission. So if we talk about 5 air changes per hour, we're talking about the reducing the risk of aerosol transmission in the far field. This dilution will reduce the concentration of aerosol in a short range or a close field, but we really don't know and cannot estimate whether that will have any effect on reducing the risk. It will also depend on the air distribution in space and so on and so on. Because basically, in a space, the loss rate of the virus or aerosol that contains the pathogen will be obtained by generally 3 methods. Will be by dilution, that is occurred by the outdoor air, and or by natural virus inactivation. Chris was talking about it, I just repeated, and the deposition. So this is where, this 5 or 6 air changes per hour is just basically a lot additional to other loss rates, such as deposition or a natural inactivation. And instead of using only outdoor air, because we are talking about aerosol, what we can do is basically replace part of the outdoor air with the air cleaning methods. That will, on one hand, reduce the level of aerosols, so dilute them, or remove them from the space, or basically inactivate the virus. And this inactivation level would be corresponding to certain loss rate of the virus in the space. So this is why air cleaners are important in that sense, because we are talking about the pathogen and aerosols. And removing it from the or reducing the risk does not necessarily require only outdoor air to be used for that purpose. So basically, to repeat, the basically air cleaner, what it does, it's increasing the dilution rate. So it's an additional loss rate or dilution removal element in a space. So if we have a mass balance model, we have emission side, and then we have a dilution side or removal side. When we have an air cleaner in a space or in a recirculation duct, whatever, we will have an additional term, and this additional term is basically on the dilution part. So this is the general theory of this. And then, of course, increasing loss rate, as is seen on the right figure, will reduce the probability of infection. So if we can document that the air cleaner is contributing to the lowering loss rate of the virus, we will then, of course, reduce the probability of infection of the virus. If we speak about air cleaning technologies in connection to the infection control and risk, and then controlling the risk of infection, we can talk about two types of air cleaning technologies. One, technologies that I would call them subtractive technologies, and the technologies that remove the virus from the space, and then will be other technologies that I would call additive technologies, that would basically add some constituents to the space to remove the aerosol or inactivate the virus in a space. So basically subtractive and additive. And subtractive, as an example of subtractive technology, we can have filters, particle filters, electrostatic precipitators, sorbents. From time to time, UVGI is also considered that, or UVC, although I would rather call it the additive technologies. And additive technologies would be the technologies that use the ionizers, bipolar ionization, needle point discharge, ozone, plasma, hydrogen. They basically add an element to the air in order to achieve the air cleaning effect. For the subtractive technologies, once again, subtractive technologies, which is filters and sorbents, there is a good deal of standards that define their efficiency. So we will know, particularly for particle filters, we can estimate their efficiency, and there is a good deal of standards to which we can refer, and we can test how effective they are. And also we have some standards regarding sorbents, but basically these are standards that refer to the material that is used in the sorbent. Also, we have standards for the UVGI. However, we have less information about other types of technologies and other standards. And particularly that applies to ionizers, plasma, and so on. There is no standards to which we can basically use and refer. And there's no rating. And then some of them, they emit ozone, and basically they refer to we can refer to UL 2998, which actually defines that air technologies, according to 62.1, should comply with that. So they should actually emit 0 ppb ozone if we follow that recommendation of a standard 62.1. There are other recommendations, though, regarding air cleaners. So although there are no standards, there are certain position documents and recommendations, and also our epidemic task force had it as a recommendation, is how what type of air cleaning technologies can be used, and if they are used, what procedures they should comply to. And this is the two positions from the position document on filtration and air cleaning that was published by ASHRA in 2015, and the new version will be coming later this year or early next year. But those two specific positions will be retained in the new version. And then, so if we think about air cleaners in connection with infection control, we should remember that all filtration and air cleaning technologies should be accompanied by data documenting their performance regarding removal of contaminants, and they should be established on industry test standards. That very often they are not available for some of the technologies that I mentioned, so there must be scientifically controlled third-party evaluation and documentation that they are working. They cannot be claims that they are working, that they should be documented. But even this documentation may have problems. I'll come back to this in a moment. And then devices that use reactivity of ozone for the purpose of cleaning the air should not be used in occupied spaces. And I will come back to this in a moment. So let's start with the air filtration. There's not much to say. Every one of us know the virus has a certain size, the droplet has a certain size, and thus we are talking about the respiratory droplets, which are 5 to 10 micrometers and lower. So the filtration will be very effective method of removing those aerosols from the air. And the recommendation that is given is MERV 13, because you can see for the MERV 13, most of the droplets or aerosols in the size of 5 micrometers will be removed. And then, of course, the best recommendation will be to use HEPA filtration, and HEPA filters will remove most of the particles from the air, but of course that will be also costly and also require specific solutions, because HEPA filters create a very high resistance in them. But generally, MERV 13 filters would be very effective. And then you can think about, can we only use MERV 13 filters? So basically, ASHRA recommendations for MERV 13, for example, can be obtained by combining filters. So combining filters with a lower efficiency will end up with a filter of efficiency of MERV 13. And this is a few examples of how you can achieve that were calculated for the example. During pandemic, portable air cleaners became very, very popular, and so-called do-it-yourself portable air cleaners were very much recommended. And especially the Corsi Rosenthal, this is just an example of this, is one of those examples where you can basically build your filter and put it in the space where there is a potentially increased risk of infection. However, we have no field evidence that that would work. We have only evidence from the modeling. So basically, we recommend use of those filters, and the filters are used, but we have no field data that would provide information that that would be effective. So we can expect that this is effective, but we cannot validate this. This does not mean that they are not effective, but I'm just saying that what we're really missing in the chain of all this recommendation is the actual validation. And this validation is not existing. This is an example of modeling. We have mainly modeling data. And this modeling data have also many limitations. I don't want to discuss those modeling limitations, but this is one of the first modeling limitations that was published at the outset, maybe, of the pandemic, in which the effects of improved filtration, we can look only on without mask, was modeled using Wells-Riley model. And then you can see this is a relative risk of infection change, relative. This is not absolute risk 100. It's a relative to the reference, which is 3A, which is the reference case, which is the ventilation of 7 liters per second per person with MERV 8, which is the classical 62.1 maybe system with designed after 62.1. So here we see a very strong effect of filtration through the modeling, but we don't have that evidence from the actual measurements in spaces. The only field validation that we have today was published last year. This is a study of in schools in Marquette region. There's also a lot of debate about this study, but if we are talking about the field validation, it's the only study that probably measured the incidence rates in classrooms of pupils after intervention. And the intervention was installation of the air ventilation, improved ventilation, mechanical ventilation systems in 300 classrooms. And then they were measuring incidence rates in those classrooms and compare it with 3,000, I think, classrooms in which no mechanical ventilation rate was used. And then they observed significant change of the incidence rate per 1,000 students. You can see here, basically, that the incidence rate is lower when there is installed mechanical ventilation system. This graph also presents the monthly incidence rates in the region. So just to compare the numbers. From this study, they proposed the number ventilation rate of 14 liters per second per person, between 10 and 14 liters per second per person to be used. And then if we compare it with the Pfeiffer changes per hour, I don't know how it would be comparable with Pfeiffer changes per hour, but this is more or less the rate that was proposed by Billings in 19th century when the tuberculosis was there was a tuberculosis, increased incidence of tuberculosis, and that was also presented in the first presentation in the session today. So we really don't know against which number we need to compare. We really don't know whether 14 is enough liters per second, 15, 20, 30, 50, and so on. So the numbers that we see are from the models based on the certain assumptions. And again, I want to repeat, this does not dismiss this data. That's only creates the situation that we try this and we must validate this. So basically, we have to make certain investments and test this. Otherwise, we will have debate all the time whether this is correct or not correct. Anyway, I want to continue. So there are other types of air cleaners, and this is basically those additive air cleaners. And I really represent what is happening here, and I want to discuss more about this. So basically, they have different names, and but they have the similar mechanisms. They create reactive ions, oxygen reactive species, or ozone, and so on, and add them to the air, and then free radicals or ozone cause that the virus is inactivated or killed, basically. And yeah, we do not know what the reactions are happening. We know that the virus is killed, but there are many other things that are happening, and often there's some of those effects may be even unproven, or we don't know whether they are safe, even, because we don't have any reference to which we can compare that. UV and GI was discussed, so there are certain challenges here that I want to discuss in the last 5 minutes, which are the most important parts of that presentation. Is that first is discussion about the efficiency of the air cleaners, then the production of those reactive species and chemical transformations that are occurring in the space, noise, and noise with respect to the cleaner delivery rate and efficiency. But there are also other aspects that I will not have time to talk, is the commissioning, maintenance, operation, monitoring, documentation. There are issues that are related to the air distribution in a space. replacement of filters. So if the system is designed for MERV 8 and you put MERV 13, you will probably need to rebalance your system because the filter MERV 13 may be bypassed. And if you put HEPA, also there may be bypass. So basically this, and also there is an energy aspect, and I will also talk about this in the end. So let's start first with the clean air delivery rate. Often the producers of the air cleaners provide us with the efficiency. So what they do is they test the air cleaner and they say that they have 99.99% removal of the whatever specimen that they test. Here we would talk about pathogen. So depending on the chamber in which this data was obtained. So this is the methodology that is used. It's basically tested in a different size of chambers. That would correspond to the different clean air delivery rate. So if this is a chamber of 10, sorry for the metric is 10 cubic feet, then clean air delivery rate will be 3 CFM, which is 1.5 liter per second. If it is 100, it will be 15 liter per second, or 1,000, it will be 150. So, and this is what is important. Important is not the efficiency, but important is clean air delivery rate by this. So there is a wide range of clean air delivery rates that can all claim 99% removal. So it doesn't mean that this will be effective when installed. So let's take an example. So if we have we test the air cleaner and it has a 98% removal in 60 minutes in a chamber of, let's say, 14 cubic meter, the effect size will be around 2 air changes per hour. But if we scale it up to a normal classroom, then the effect will be only 0.31 air changes per hour, clean air delivery rate, which would mean that to get 5 air changes that is recommended by CDC now and also by Lancet Commission, you'll have to have 16 units in a classroom. So 1 unit will be not enough, and then you have to have 16 units in a classroom. More about this you can read in the very nice paper that was published in ASHRAE Journal, that is actually discussing the how to interpret this air cleaner data. The study was made by Stevens and others, and it can be obtained from ASHRAE. The whole point is about a removal effect and effectiveness, and that we really don't know. We really know it from the theory of air cleaners. Is basically that efficiency. You always have to compare the effect that is obtained by the air cleaner in comparison to other removal effect. So, and in case of the air cleaner, we speak about efficiency and effectiveness. And effectiveness is a term that is actually telling us how effective the air cleaner is in comparisons to other methods of removal. And if you have efficiency of 99%, but very low clean air delivery rate, the effectiveness will be very, very low. So basically, there will be no point of using the air cleaner. Yeah, I will quickly. Okay, how much time I had actually? Okay, sorry. So now very quickly, ozone. So ozone, there are data on ozone that are presented, and the threshold for ozone suggested by the SAM standards are 50 or 20 ppb. By presence of ozone will produce the basically they will cause incomplete oxidation of many compounds, and then new compounds will be so ozone production in the process of killing the virus or deactivating may produce some toxic pollutants. I will quickly. There are new papers that show that even UVC may produce excessive levels of particles in the space. And then there is also a new paper published recently on the toxic pollutants that are produced through the gaseous as a secondary air pollutants through the reactions with ozone. Then there is a point of noise. So if you have a noisy, if you have air cleaners which are portable air cleaners. Here you see this is a test that was done in Denmark on 27 portable air cleaners and looked at the effect of the air cleaner in terms of cleaner delivery rate and noise. So I come back to the example of 64 air cleaners in a classroom, and most of them will have to run to have any effect at the noise level of 50, 60 dBA. So that is another problem. I'll skip this. So I will just go to the take-home messages. This is a strong personal bias. So air cleaning as a measure to reduce infection rate. So we should use outdoor, yes and no, because sometimes the outdoor air may be polluted. And then air cleaning and filtration should be used to reduce infection risk. Yes or no also answers. So some technologies are useful and some of not. MERV 13 and higher should be used. Portable air cleaners with HEPA, probably yes, but we have to remember about the noise. The new evidence with of the secondary aerosols produced by UVC is now we have to be tested further, but probably yes, because this technology has been used, UVGI. Additive technologies and reactive species probably no, because of the negative consequences that they may bring. And then the problem of the is that we have a lack of proper testing methods and a lack of verification in actual applications, and we have to weigh risks. So maybe some of the technologies, even though they may produce some toxic pollutants, the levels may be very, very low compared to the positive effect that they produce during pandemic. So that is, we don't know about this. So thank you. Sorry.
Thank you very much, Pawel. So this is a good strategy to pass off 7 minutes the time you are allowed to avoid question, but we will come to the discussion later.